Thanks to Yulia and Hannah as well for arranging the seminar tonight. Well, this morning. Tonight, to me, as you can see, if you can see behind, I don't know if you can see me, but if you look behind me, you can see that it's become quite dark outside because the sun has just set. But I can tell you where I am in this first slide. I'm actually in that room in the top right-hand corner that I'm pointing to at the moment. And the lights are on and I'm home at the moment. So let's have a look at the talk. I'm going to talk about diffusion limit of Wright-Fisher models, definitely. Whether I get to the branching models or not will depend on how fast I go through this. So we'll see. I'll definitely do the first part on the Wright-Fisher models. Okay. Now, I'm just trying to work out. Yes, that's worked. Part one, the Wright-Fisher model. I imagine I probably don't have to spend too much explaining what the Wright-Fisher model is. I'm going to just look at the simple haploid case and assume first slide is mainly just to establish the notation, some fixed size population, which we'll call N. And the Wright-Fisher model is defined over finite time steps. So as we go from time step tau to time step tau plus 1, you have a population. I've got 10 individuals in the population there. We've got 7 of them are of allele type 1, 3 of them are of allele type 2, and after one generation, we've moved from I equals 7 down to j equals 6. So you can see it's quite simple. It's defined so that every individual randomly picks their parent from the previous generation. Every parent has an equal chance of being picked, and you inherit the same color allele as your parent. And that leads to this nice binomial distribution for the probability of going from I type 1 alleles to J type 1 alleles. And I imagine you've probably all seen this one. I over n is the chance that your parent is of type 1. 1 minus I over n is a chance that your parent is of type 2. You need the factors of j and n minus j up here to account for the fact that we've got n type 1s, n minus j type 2s, and there's a combinatorial factor. And as you probably know, if I set this off, sooner or later, either all the type 1 alleles fix or all the type 2 alleles fix throughout the entire population. So it's not a very interesting model at this point. You can calculate things like how long it takes for the allele to fix. But other than that, not a lot you can do with this as it stands. So you need some dynamical way to introduce mutations into the system. So we'll introduce 2 more parameters. The probability of mutating from type A1 to A2, I'll call R12. Probability of mutating from A2 to A1, I'll call R21. And so there's a mutation from 1 to 2 on that branch. And over here, there's a mutation from type 2 to type 1. And when you introduce those mutations, you have to make changes to the transition amplitude of this. This is a Markov chain transition amplitude. You have to make changes to that transition amplitude because the probability that your parent is of type, the probability that you are of type 1 when you were born is a sum of 2 probabilities, the probability that your parent's of type 1 and there's no mutation, or the probability that your parent is of type 2 and there is a mutation. So you plug those things in and you get a transition probability for a Markov chain. So I've got a simulation of this on the next slide. I hope that's big enough for everyone to see. I've got a tiny little population size of just 10 here, and I've taken this for 40 generations, and I've started off with everybody is of type 1, that's the red alleles, and every now and then there's a mutation to the blue alleles, and it either spreads through the whole population and fixes, or it just dies out, as it has here, it just dies out. Now, there's not a lot you can do with a discrete model analytically as it is, and this is why we like to look at the diffusion limit. And the diffusion limit is defined like this. You let the population size become very big, you let the mutation rate become very small, and you do that in such a way that the product of the two gives you a little 2x2 mutation rate matrix. And at the same time, you take the time axis and you squeeze a lot more generations into the same physical time. So we're going to, in this case, going from the first simulation to the second simulation, 5 times the population size, 5 times as many generations, and 1/5. The little mutation rates here have gone down to 1/5 what they were before. And so this quantity Q here has remained fixed. And we can take this one step further, another factor of 5 in the population, another factor of 5 down in the mutation rates, and another 5 times as many points squeezed onto the time axis. And we've really approached, we can see we've sort of approached a stage where we've got essentially a continuum time. You can think of the quantity of, or the proportion of the population who are of type 1 as being a continuous random variable now between 0 and 1. I had to run this simulation a few times because I've got a fairly small mutation rate here. Even though it's small, it's actually unreasonably large compared with real mutation rates in the real world. And think of these as neutral mutations. There's no selection built into this model. These mutation rates are normally much, much smaller than that. But you can see I had to run this a few times to get a nice example of a substitution happening throughout the entire population. But you can see the sort of time, typical time over which substitutions happen on that time axis remains fixed when we take this continuum limit. So this is how the diffusion limit works. The idea is to scale things in such a way that you maintain the general sort of behavior of the system. And you'll also notice that these boundaries become very fractal as well. So if we look at the next page, sorry for the non-mathematicians in the audience, but this is where the equations start. I'll try not to overload you with too many equations. So here's the diffusion limit all written out again at the top. We've seen that already, and we showed you that in the illustration. There are 2 ways to describe this. Well, there are many ways to describe this, but there's 2 ways I'm going to talk about. One I'm not going to talk about for the rest of the talk, but I'll just sort of mention it briefly. If I call the number of red alleles in the population y at time tau, y can run anywhere from 0 up to the population size n. If I divide y by the population size, I get a number between 0 and 1. And in the diffusion limit, that number becomes a continuous random variable that sits on the range from 0 to 1. And the first equation is a example of a stochastic differential equation. And it tells me if I have an increment dt in time, what sort of increment is likely to happen for dx. And there are 2 parts to the equation. The first one is the one, whoops, I can't just highlight the first top line, I don't think. No, I can't. The first line there is basically the driving term that pushes the mutations happening in one direction or the other. The second one is the random noise you get from genetic drift. And dw here is called a Brownian motion. In time dt, the corresponding dw is a random variable. It's a normal random variable. It's got mean 0. It's got variance dt. And it's basically saying, look, when things change, you get this jiggling behavior. You get this nice fractal jiggly lines running down here. So this form of the writing down the diffusion limit is quite useful for doing numerical simulations, for instance. What I'm going to concentrate on more, and it would be easier to see if this black rectangle wouldn't keep turning up on the bottom of the screen, but I happen to know if I click on that X, it's going to close the window down, so I'm not going to do that. The equation down the bottom, and I'm highlighting things accidentally here, which I don't want to, is an equation in terms of the probability density of this random variable X. So this f subscript x at any particular time t, you could cut through this diagram at some time t. Supposing I started off with some particular initial condition, and here I start off with the initial condition that x is all concentrated at x equals 1. In other words, everything is of allele type 1. The density is the density defined over the argument x runs from 0 to 1. T is the time running down the page, and it starts off as a nice sharp spike at x equals 1, and as time progresses, that sharp spike is going to spread out to look a little bit like you imagine a sort of a delta function that spreads out like a bit like a normal distribution to start with, and then it spreads out more, and it eventually settles into some sort of stationary distribution afterwards. So there are two terms on the right-hand side. The first order one is the one that corresponds to the forcing term, pushing the mutations one way or the other. And the second term on the right-hand side is the one corresponding to genetic drift. Now we can solve that equation. This is one reason we go to the continuum limit, is whereas the original discrete model it wasn't possible to solve that, we can actually solve this differential equation. And what I'm going to show you is the stationary distribution, which is well known. It's actually been known for a very long time. The stationary distribution is a beta distribution. So x runs between 0 and 1. The red line here, just ignore the vertical black lines for a second. The red line, you can see it running along the bottom there, and it runs up and it shoots off to infinity at both ends. The red line is the beta distribution. It's this function here plotted out. Don't worry too much about the C. That's just a normalization to make the thing have integrate up to 1. So basically, this probability distribution, the stationary distribution, has the following meaning. It means if I let this system run for a very long time, and I sample the population, what's the probability that, say, a fraction, well, somewhere around here, 0.4 maybe, of the population has, that the population, 0.4 of the population is of type 1 and 0.6 of it's 0.2. Well, there's some tiny little probability here. It's not very high at all. The population spikes at the end because when you sample the population after a long time, you'd hope that the entire population was of the same type. After all, you don't want every site in the genome to be a SNP. You would hope that most of the sites in the genome are non-segregating, so you'd like them either to be mostly of type allele type 1 or of allele type 2. The red curve is this function you get from the continuum limit. The black vertical bars I've drawn are a simulation I've done with a population, a finite-sized population of 100 and some finite values for the mutation rates. It's difficult to see how good the fit is. I've drawn it on the next slide as well on a log scale. And you can see that even for a small population size, the continuum theory really fits extremely well to the diffusion limit. So not only does the diffusion limit give you a nice way to do the mathematics, in the case of 2 alleles, it enables you to actually get an analytic solution. It actually gives you a very accurate approximation to a finite-sized population. Okay, well, everything I've told you, I've probably wasted the time of anybody who's a theorist, because you'd already know that, and you'd know that it's been known since Wright published this paper in 1930, and this is a picture of what he calls site frequency spectrum. It's basically what, or actually, sorry, I don't doubt that he would have called it site frequency spectrum. It's actually basically a plot of the curve I just showed you. And if you look down the bottom in the footnote here, I've blown it up big. Look, here's the beta distribution. The notation's different from mine. I've got x's where he's got q's, and he's got n times v and n times u where I had the mutation rates at the top. So all of this was known. So what have we done that's new and different? We've extended this to multiple alleles. Pardon me, I'm getting a dry throat. I've just got a cup of tea here, so I'm just going to have a swig of that. Okay, back to the talk. We've got multiple alleles, and instead of just 2 mutation rates, these are continuum mutation rates that take you from allele type 1 to 2 and from 2 back to 1, we've now got a 4 by 4 mutation rate, if we think of the 4 alleles as, well, what's the letter at a particular genomic site? It can be one of 4 types, A, C, G, or T. So you can put together, I won't write out the discrete form of the transition amplitude. It's a bit of a messy formula, but take my word for it, you can write out the discrete form of the transition amplitude. You can run a simulation, and here's a simulation where I started, everybody was a type A in the population, and I ran it a few times so I could get a nice example of a substitution event, and you can see that there's a T allele fitted in one individual in the population, and just through genetic drift, it's managed to drift through the entire population, and the allele T has fixed throughout the population. So this is the sort of thing we'd like to model, or at the very least, we'd like to be able to look at that stationary distribution. Okay, so this is some nasty mathematics again. This is the forward Kolmogorov equation. I showed you this. This was the evolution equation for the density function that I showed you before, the density function f. It becomes more complicated when you've got more than one allele. I'm going to assume that the number of alleles is a number I've just called k. I'll keep this as general as possible. So we'd have a 4 here wherever you see the k's if we're looking at A, C, G, and T. Instead of just the relative proportion of allele type 1, we've got the relative proportion of each one of the 4 types of alleles to look at. It's easier to write down the equation in terms of all 4 of them, but they are constrained that they have to add up to 1. Because the proportion of the 4 types of alleles have to add up to 1, the density F that we're looking at, I'm trying to highlight there. No, it's not going to let me just highlight the F. The density F that we're looking at is defined on a shape called a simplex, which if I had 3 alleles, it would be a triangle. If I have x1 plus x2 plus x3 adds up to 1, every point inside that triangle would be a particular value for x1 and x2 and x3. That's the proportion of the 3 alleles. In 4 dimensions, I can't draw 4 dimensions very well, but on the next slide, I can draw the simplex itself. It turns out to be a tetrahedron. So here's the equation we have to solve. Don't worry too much about the details. We have to solve a nasty partial differential equation. It's a function of both time, t down the bottom, and it's also a function of 3 of the 4 x's. The 4th one is determined by the first 3, so we really don't need to solve for all 4 of them. Now, Wright obviously thought of giving this a go, even though he didn't know about the genome and C's, A's, G's, and T's, but he thought he'd give this a go. So let's try putting in more than just 2 alleles. The paper I showed you before was 1930. By 1961, in a textbook he'd written, he was still not getting terribly far with it. He said, look, nobody's managed to solve this. We've been banging away at this for 39 years now, and nobody's managed to get anywhere with it. Not quite true. If you choose your mutation rate matrix, the Q's here, to be of a very special form, then it turns out you can solve this, and you get a particular generalization of the beta distribution called a Dirichlet distribution. So if you know the beta distribution, you may have come across the Dirichlet distribution as well. It's defined on a simplex, and it's just got a sort of a nice generalization of the formula for the beta distribution. The particular form, unfortunately, says, well, let's look at mutations where it doesn't matter what parent allele we mutated from. And unfortunately, that has no particular real biological significance. It's as if every row of the rate matrix here, every row was the same. And so it didn't matter whether you were coming from allele A or C or G or T, it would only matter what you were going to. That's not how mutations happen in the real world. So yes, you can get a nice solution in this particular case, but unfortunately, it's not a very useful case. So what have we been doing? we can't solve it in general, but we can actually solve it in the very realistic case for nucleotide transitions, where these scaled mutation rates are very small. And typically, when you take the mutation limit, you're really looking at scaled mutation rates of the order of about 10 to the minus 3, 10 to the minus 4. They're fairly small numbers. And if you do a numerical simulation, you'll find that just in the same way that that beta distribution was concentrated at the edges, the simplex, I said before, was a tetrahedron. This is a numerical simulation of the stationary distribution, and you'll find that the concentration of the probability is concentrated at the corners. And that's good news because it means that the model actually predicts that if you were to pick a site, a neutral site at random in the genome, that's been evolving for long enough, you might assume that it's settled down into the stationary distribution, then chances are everybody in the population is going to have the same allele at that point. The site's going to be non-segregating. So there's a certain probability that you're looking at A's throughout the population, or T's or G's or C's. And so that's what the first dot point here says. Most of the probability is at the corners. And that's saying that if you take a finite sample of the population, it's likely to be non-segregating, looking at the allele at a particular site in the genome. Occasionally, if you look at a site in the genome, just pick some neutral site, you'll see that it's biallelic. Some of the population is one type, some of the population is another type. And that corresponds to the edges of the of the tetrahedron. So basically what that's saying is that you've hit a point in this probability distribution sitting on the edge here, where you may have a certain fraction of the population is G, certain fractions T at that particular site. Very rarely you will get a triallelic site in a multiple alignment across a population. And that's basically consistent with the idea that there's very little probability in this distribution anywhere other than a lot at the corners, quite a bit along the edges. So this gave us the hint that, yes, we can actually get a reasonable approximation to the solution of that forward Kolmogorov equation if the QIJs are very small. And the way you take the approximation is you just assume that all the probability is just running along these line densities along the edges. So you've effectively turned the thing into a set of two allele problems where you've only got, let's just say, we want to solve the thing along the edge from T to G here. Well, basically, it's been known since the 1930s how to solve it if you've only had two alleles, and we want to solve the equation running along here. So that gave me the sort of the heuristic idea of how to solve this. So what I'll do is I'll jump right to the solution. So this is the solution. It's not the complete solution. It's only the solution for these biologically realistic small mutation rates. And what I've written down is not the actual solution for the density function. I've written down the sampling distribution. That means in the continuum limit, the population size is infinite. But of course, what you do is you go out and you sample a finite number of individuals. So we'll sample maybe 100 individuals or something like that from the population. And we look at a particular site in the genome, and you might say at that particular site, how many of the individuals are A's, how many are C's, how many are G's, and how many are T's? Well, the sampling distribution we get out of our theory when we solve it, it says that there's a very high probability that the entire population is, well, the sample is non-segregating, that the entire population is of the same type, and the other three alleles are just not accounted for at all in the sample. And that's the first line of the equation here. In the case where you're looking at one of the edges of the tetrahedron, you're looking at a segregating site where, let's say I and J would be the two alleles. It might be A and C or T and G or something like that. Yi of them are of one type, Yj of them are that type. The probability of that occurring is this line And if we're working only to first order in Q, because it's small, we're saying that you're never going to see a triallelic site, or you're never going to see a tetraallelic site. You're never going to see 3 or 4 alleles represented at a single site in your multiple alignment. So you can see the first line is of order 1. These pi i's here are the stationary distribution of the rate matrix Q. The second line is first order in Q, so you can see these numbers are smaller than those numbers. And you can't quite see it dot. There's an H in here. It's basically these numbers called harmonic numbers. It's just the sum 1 over y, 1 up to n minus 1. So that's basically what that formula says. You can look it up in our paper. So how do we get at this? How do we get at this solution? Right. Well, the first go we had, I got this solution out working with a PhD student of mine, Yurong Tang, and basically I did it by doing a fairly rough approximation of just saying, well, look, let's just assume I'm not looking for a whole density over the whole space. I'm just looking for point densities at the corner, and I'm looking at line densities running along the edges. Now, I know how to solve for the line density running along the edge. It's almost the beta distribution I showed you, but it's a little bit different because it's possible, well, the boundary conditions at each end of that edge are different. So what happens is a beta distribution, if I whizzed back, I won't whiz back through the slides, but you'd see the beta distribution looks very symmetric for very small mutation rates. And in fact, you could just write it as this first term here for the normal beta for the beta distribution, because you get x to a power something minus 1, but that something is tiny, so it almost looks just like this along the edge. So as long as you stick to first order in the mutation rates, we've basically got the beta distribution. You might have to fiddle around with the normalization, but that's basically what you've got. But if the rate matrix is not of a particular form, what we call a reversible matrix, it turns out that the boundary conditions mean that you can actually have a flux of probability running around closed loops. So this is sort of the physicist in me coming out. I'm thinking of this as sort of lots of pipes with water running through them, and whatever flows into the corner's got to flow back out again. So you've got to conserve probability at the corners. And you put that in and you grind through lots of algebra and you worry about the non-reversible part of the rate matrix, and you find that there's a second term that turns up. So that's basically the intuition. I won't go through the mathematics. The mathematics, of course, is where all the thinking part is. That was the intuition that we started with, and we were able to get basically that, work through it all, and we were able to get that. Oops, I've lost my mouse. Here it is, it's back again. We were able to get that form of the solution. The first time the reviewers came back, they said, well, it's not very rigorous, is it? So I did actually manage to do some sort of horrible asymptotic expansion near the corners and got the equations out slightly more rigorously, and that kept them happy. Okay, just in case you want to know how good was the approximation, well, here is a plot of those probability distributions on a log scale along those edges. You can see that because there are 6 edges to the tetrahedron, the red line is the solution, the blue cross is a simulation with a finite sized population, and it fits quite well. I think the mutation rates, the scale mutation rates are about 10 to the minus 3 for these plots. Okay, now, then I got to know Bob Griffiths, who's one of the sort of grand old names in population genetics. He's retired recently, and he came back to Australia, where he's from, and we got to meet each other. And he looked at this and he said, "Well, I can get these. I think I can get these solutions that you've got out rather more rigorously." And he says, "We'll use the coalescent." So the idea of the coalescent is basically it's a sampling distribution I want. So I've sampled let's pretend that variable black rectangle isn't there. I've sampled 5 individuals in my simulation, and I followed their ancestry back through these jiggly lines back through here, and it's a bit hard to see where it all goes, but eventually you get back to the common ancestor of everybody. So it's hard to see it, so I've straightened them out over here so you can get a nice picture, and this is what's called a coalescent tree. You've all seen this before, I'm sure. And what's going on in the coalescent tree is if you follow these guys backwards, it turns out that the approximation of small stopping at first order in Q turns out to be precisely the equivalent of only allowing 1 mutation in the coalescent tree. So Bob was very experienced and taught me all about how to work with coalescence. And basically, we need to know a couple of things about coalescence. One is that the intercoalescent times are exponential random variables with a known mean rate or mean for the mean coalescent time. And the coalescent time is such that the coalescent times are shorter at the bottom of the tree than at the top of the tree. So you always get this sort of coalescent tree that stretches out as you go towards the top if you have neutral mutations. And the other piece of information we needed was, well, if we put 1 mutation somewhere in the tree, we need a nice formula, and Bob had the formula for what's the probability that if we've sampled n and the mutation was at this particular point at the tree, what's the probability if I have, say, 3 individuals in the coalescent tree at the time the mutation happens, what's the probability I've got C allele types of the mutant allele in my sampled population at the my sample at the bottom. And there's a nice formula for that too. So these are the sort of pieces of information you put into the calculation. The other thing you have to do is you interpret the mutation rate matrix as a product of 2 things. There's an effective Poisson process theta that basically says, look, every time there's a mutation from one site to another, from one allele to another, we think of this as a Poisson process where there's an event happening. And on top of that, we'd like to know how we're moving, which allele we're moving to. And it turns out that if you take the right combination of the rate matrices, you get a finite state Markov chain. And as you jump from one site to another, the Markov chain's jumping around. Unfortunately, the horrible black rectangle sitting on top of this one, and you can see that as I go from A to G to T, you're missing the fact that there's a little loop around a T before you go back to C. When you use this particular formalism, you find that it puts in some extra fake transitions that aren't actually there. There's one just there, which didn't actually happen. But it doesn't matter. We know how to cope with all that in mathematics. So you put it all together. This is the answer that comes out. This is the equation I showed you before. Essentially, it's a nice diagrammatic expansion. It says, look, if this is a coalescent tree, there can be no mutations, in which case you get the first term. Whoops, you get the first term here. Now I can't highlight just that pi. There could be one of these these silent mutations, in which case you get the second term here. Or there could be a real mutation, in which case it leads to the next term here. So you have to grind through the algebra, but take my word for it, it all comes out quite nicely. Bob, being Bob, wouldn't leave it at that. He had to say, well, look, we can also use the backward generator. I won't inflict the algebra on you. Let's just say there's a third way to do it. Okay, and you grind through the algebra and you look at expectation values and so on, and bingo, the answer comes out yet one more time. Okay, there's a 4th way of doing it, and I've lost my mouse again because I've got 2 windows open, and I keep accidentally going on to the other window. There we go. Dominic Schrempf and Asger Herboth, who I believe, what's it, Dominic, I think may have been at your university in Vet Med Uni
Yes.
at some stage, had already put together a nice model for the two allele case, putting in not just the neutral case, but also selection as well, and they've done quite a bit of work on that. And they took my my first solution before Bob and I worked on it, and they actually managed to put their attack the problem with their boundary mutation model, where the mutation dominates at the boundaries, and if you're inside the simplex, then you're only looking at genetic drift, and you actually come out with the same solution once again. So there are we've got more ways of deriving this sampling distribution than we know what to do with. Okay, so we've got the sampling distribution. That's the story so far. So what did Klaus and Lynette do with this? We actually applied, I'm a mathematician, so I'm absolutely lousy when it comes to actually applying things to real data. But luckily they had some real data, and we looked at the sampling distribution, and we did quite a nice calculation of estimating the mutation rate matrix from a multiple alignment of neutral sites. So the idea is you have an alignment of neutral sites. Most of the sites are non-segregating. Every now and then you're going to get a biallelic site. There are so few triallelic sites, you can just chuck them out of the data. You can throw them away without really doing too much damage. The only data you need to collect, actually, if we have typically the number of individuals would be somewhere between 10 and 1,000, at about 100 typically. Quite a large number of sites, maybe about 10,000. The only data you need to collect is the number of non-segregating types of sites of each type, and the number of sites for which are biallelic, and for which, between say type A and type J, for which there are Y of type I and N minus Y of type J. So these numbers basically tell you everything you need to know in order to estimate the mutation rate matrix from a maximum likelihood calculation. So there's another little diagram of what these L's mean. They're basically the counts of how many times you're at the corners and how many times you're along the edges. Okay, so how do you do a maximum likelihood? Well, you've got to write down a likelihood. It's basically just the probability of seeing the particular combination L of these random variables for a given rate matrix Q. You turn it round backwards, so Q becomes the variable, L becomes, rather than the parameter, and L becomes the parameter of your calculation, and you maximize as a function of Q. Sounds easy, but it turned out to be algebraically quite more difficult than you might think to start with. The form of the likelihood is a multinomial, which would be easy to estimate the parameters for, which would be the p's in an ordinary multinomial, except that we don't have as many independent values of these probabilities as there are elements of the matrix Q. And because of that, you've got to use more clever methods, which I'm afraid I'm not going to go into in this talk, because the non-mathematicians would probably lost enough already. Okay. So you can do this various levels of complication in this calculation. You can just let the rate matrix be as totally general as possible, in which case it's a 4x4 matrix, but 12 of the elements are independent, because the diagonal of the matrix is determined by the off-diagonal elements. You can say it's a reversible rate matrix, in which case only 9 parameters have to be estimated. Or you can use strand symmetric, which says if I swap around A's and T's and C's and G's, then the data should be, on average, insensitive to that, to swapping, to making these transitions. And that only gives you 6 independent parameters. And bingo, here's the data set we started with. It was short autosomal introns. I'm glad the experimentalists know what some of these words mean. Drosophila, I know what that is. It's fruit fly. I've got them growing in my compost bin at home. 197 of them. 200,000 nucleotides, which are believed to be neutral if you pick the right sort. Gives you a nice big table of the data, the non-segregating sites up here. Oops, that's the first row, and the site frequencies of the segregating sites. These are the estimates that come out. They're basically just 4x4 matrices. What you get out are basically these scaled mutation rates. So it's the per generation mutation rate times the effective population size. So to turn this into a per individual per generation mutation rate, you also need to put into this calculation an effective population size. So this is after that's been scaled out. So we get different results depending on what form of the rate matrix we use. There's a statistical test you can do to see whether the extra degrees of freedom are significant, and you find that yes, indeed, all 12 parameters of the rate matrix are significant for this data set. That if you think that you can just get away with saying, well, actually, we think this might be a reversible rate matrix because the maths is easier, or we think this might be strand symmetric, it turns out that no, this particular data set, it looks like you need all 12 parameters, are quite significant. So that's basically summing up the first part. I don't really have much time to go through the diffusion limit of a branching process. Maybe, can I spend about 5 minutes just giving you a flavour of it? I'm not quite sure if we need time at the end for questions or not. Is there an opinion about that?
It's fine. Just go ahead. We can continue a quarter of an hour afterwards.
Okay, fine. Okay. All right. I just need another drink of tea, so my throat's got a bit dry again. Okay, we're back again. Right, how does a branching process? Well, this is what's generally called a Vienna-May Galton-Watson branching process. Galton and Watson published the idea first way back in the 19th century. They were predated by about 20 or 30 years by a French mathematician called Vienna-May, whose name I'm probably pronouncing completely wrongly. But he didn't publish. So, but it's known that he studied this branching process first because there's correspondence that he wrote to colleagues about it. So people quite often just call it a Galton-Watson branching process, unless they're French, in which case they insist on that you call it a Vienna-May branching process. Okay, so you've got, it's a bit similar to Galton-Watson again, except there's no restriction on the population size. You don't pre-specify the population size at all. It's a stochastic process where discrete time steps, at every time step, each individual has a random number of offspring, and the number of offspring, I'll call it a random number S. It's non-negative integer valued, so it takes the values 0, 1, 2, 3, etc. 0 has to be included in this calculation, and the reason for that is we have to be able to allow the population to go extinct. It can happen that the entire population, nobody has any offspring, in which case the population has become extinct, and that affects the dynamics quite strongly. So once again, we define a random variable. I'll call it y of tau. It's the number of individuals at each time step. So in this diagram, we start off with 5. The each individual little family, by the way, is independent. So the fact that this individual had 2 offspring doesn't affect the fact that this one had no offspring. So we go 5, 9, 11, 12, 14. You can see this population's growing. What we're looking at, you guessed it, is we're going to put 2 allele types into this, which is something Galton and Watson didn't do. And we're going to look at the essentially neutral mutations once again. We put in a mutation rate from type 1 to type 2, and a mutation rate per time step type 2 to type 1. And every now and then a mutation happens in the generation, in the system. And after a number of time steps, you'd like to know what's the, whoops, I can't highlight just the bottom row there, no. We'd like to know just what the distribution of allele types is. And once again, you can take a diffusion limit of this system. So what I might have time to do is just go through how the diffusion limit looks if you only have 1 allele type. And this particular problem was solved back in the 1950s by a probabilist called Feller. So what I'm telling you is actually fairly textbook stuff. So we start off with, this is just 1 time step. We're assuming that the probability of having no offspring is positive. So here's somebody who had no offspring. Here's somebody who had 3 offspring. We're going to assume that the expected number of offspring is some number lambda, and it's called subcritical if that's less than 1, which means the population tends to die out. Critical if it's exactly 1, and supercritical if it's greater than 1, which means the population tends to grow exponentially. You can't quite read there, but the defining formula for this is that the population size at time tau equals tau plus 1 is basically the sum of all these s's over the population size at the previous generation. So you just add up the number of individuals that each parent of the previous generation produced. Okay, so that's enough to define the whole system. Here are some nice simulations. I always like to show simulations because they really give the game away. It's not surprising. You can calculate if your process is, subcritical. It's not surprising that the mean of the distribution is basically an exponential function dying away. Exponential, not growth, the opposite, decay. There's about, I think I've got about, I've shown about 50 trajectories of this system here. If the mean is 0, so we're looking at the critical system, the mean of the distribution stays constant, and if lambda is bigger than 1, it grows. And I've picked cases here where the mean of the distribution is very close to 1, and the initial population size is very big. And that's actually how you take the continuum limit, the diffusion limit. You let this lambda go to 1, or log lambda go to 0, and you let the initial population size become infinite. That's the trick. So I'll look at the supercritical case just quickly, because that's the one that's easiest to understand. If I run a supercritical case as a simulation and draw a histogram at some later time, I find that the histogram consists of 2 parts. There's a nice smooth distribution, and there's a spike at 0. And the spike at 0, it's basically any of these trajectories that went extinct. Once the population goes extinct, it stays extinct forever. Because there's nobody left to have any offspring, of course. So you get this funny sort of function, which is a continuous distribution, and you get a point mass at 0, or sorry, I'm talking about continuous and point masses because that's what happens after you've taken the diffusion limit. You get this spike at 0. So this is how you take the diffusion limit. Big population, and you let the expected number of offspring get very close to 1, so the log goes to 0. And you need a continuous scale time, as we did before. You need a continuous random variable to describe how big the population is. So you scale it by the initial population. It turns out that the 3 parameters in the problem, the initial population size, the expected number of offspring, and the variance number of offspring, can all be bundled together into one parameter called alpha. And you do the diffusion limit, you get a nice forward Kolmogorov equation, a nice partial differential equation for the evolution of the density. And this is what the solution looks like. You're thinking, yeah, there's a lot of symbols on the page there. I'll just concentrate. There's 2 forms you can write it in. I'll just do the first line. We'll ignore the second line. You don't want to know about modified Bessel functions. No, of course you don't. There's a piece to start with, which is the probability that the whole population goes extinct. And it's got this spike. It's a point mass at the origin. And there's a piece here which you can interpret as, well, if I could draw the coalescent tree of the population running back in time, I would find out that not of the original population, most lineages actually died out, and I'd have a finite number of families that the population started from. And this is actually a sum over those family sizes of the initial number of progenitors of the system who didn't die out. So there's a nice sort of interpretation for this messy formula here. What's probably easier to get your head around is, well, this is what the continuous function looks like. And you can see it fits the simulation very well. I can't draw the spike because it's actually a red line that goes up to infinity up through the roof of the building. But basically it fits, the theory works. And this solution was found by Feller back in the 1950s. So we would like to do a similar thing when we put the mutations in. And that's probably more than I've got time to talk about. I'll just mention very briefly that the one case that we would like to do is the subcritical case. And we're doing the subcritical case where you condition on survival. So the population goes extinct almost surely. But if you cut this off at any finite time, there's a few runs that didn't go extinct. So there's a finite probability that you don't have extinction. And you can condition on the event of the population not going extinct. And you get a distribution that looks like this. So I started off with a huge number, 20,000 trajectories actually, and a few hundred of them managed to survive out to time 300 here. And you do the conditioning, you can work through a calculation, and you can get down to this distribution here, which is the, basically you go through the algebra. It's when you condition on non-extinction, it's called a Yaglom process named after a Russian mathematician, and you get a particular solution for this distribution. It's a nice exponential distribution, and of course, it fits very well. And the reason we're doing this particular case is because it's a case where if you put the allele types back in again, if you look at the supercritical case, it turns out that you get this fixation. You get one of those allele types fixes in the population again. So the stationary limit's not very interesting. But if you look at the subcritical case, you find you do actually get an interesting limit at the end. And so I've not got time to tell you what that limit looks like. I've probably got time to just to show you, hey, look at my plot. It looks very good. That's a simulation. These are these curves running through here are nice. So that's just the flavor of what we're doing. We're writing the paper up at the moment, and it'll be ready probably in about a month from now. So over the years, I've written a few papers. The first 4, I think the first 3 of them, and the last one here are the first half of the talk, and the other papers 4 to 7 are all about branching processes. Here are my collaborators over the years. Bob Griffiths and Klaus and Lynette, you know, and graduate students I've been working with. And I think I'll stop at that point. So thank you very much. And outside it's become quite dark, so don't believe the picture, but I'm still in that room in the top corner there. Thank you.